Morning, everyone. So we left off last time and we had talked about mass percent and its relationship to chemical formulas, and how if you have a chemical formula, it's actually quite easy to find the mass percent, right? You just take the part divided by the whole and multiply it by 100. You guys hearing me? For whatever reason, it says my Zoom is not registering. Elizabeth, can you hear me? Carrie, you can hear me? Okay, cool. Well, we'll just go with that. If you have the right empirical formula, you can find the mass percent by taking the part element divided by the whole mass of the compound and multiply by 100. And then we went the other way too, where we were able to take the mass percents and come up with a correct formula. There's one more element to this lecture that I want to go over, because everything that we had been solving had been empirical formulas, right? It's the lowest ratio. Well, what if we're given an extra piece of information about the molecular formula? So, slides up. Thought I had them open already. While I'm waiting for the slides to open up, I want you, just as a refresher, to do one more empirical formula. So let's get you to do this first one here, number 1. So it says, what's the empirical formula of a molecule containing 65.5% carbon, 5.5% hydrogen, and 29% oxygen? 65.5% carbon, 5.5% hydrogen, and 29.0% oxygen. So I want you to come up with an empirical formula. We will go over it in about 2 minutes, and then we will build on that. And then it'll be the end of chapter 6, which just seems to last forever, every semester, such a long chapter. Okay, so anytime we have a problem where it gives us percentage, we can assume 100 gram sample. We can literally just take that percent and put it into gram. Now you can't take that percent and put it into mole. That's something that we will have to convert. So we can change it to gram, and now we're going to convert all of these into moles. So 1 mole of carbon, 12.01 grams. 1 grams of carbon. 1 mole of hydrogen, 1.01 gram of hydrogen, 1 mole of oxygen, 16 grams of oxygen. So this first one, I get 5.45 moles carbon. This next one, I get 5.45 moles of hydrogen. I like that those are like a similar ratio, right? This last one is what, 1.81 moles of oxygen. So this is the correct ratio, but they're not whole numbers. So we want to get it into whole numbers. The fastest way is to divide it by everything by whatever the smallest decimal is. So in this case, it would be the 1.81, 1.81. 5.45 divided by 1.81. Let's hope it's a whole number. It is like 3.011. That's close enough to 3. Okay. So this is 3, this is 3, and this would be 1. So our formula, just go in order that they list them. So we'll do carbon first. So C3H3O. This is the empirical formula, right? Lowest ratio. Well, remember that there are also molecular formulas out there. So the molecular formula is what's actually happening in real life. So in real life, there may be more than, you know, a 3:3:1 ratio. There may be like 6:6:2. So what you would do is take whatever your formula is. In this case, they're using CH2O. The one we had on the other page was C3H3O, just so keep them separate. But so we've got a molecular formula for, let's say we've got CH2O. The molecular formula is going to be that thing times some value N. Now, what is N actually saying or standing or representing? It's like how many times bigger is the molecular formula than the empirical formula. So is the molecular formula twice as big? Is it 3 times as big? Is it 10 times as big? That's what your N value is. So if it was like 2 times as big, right? If the molecular formula was twice as heavy as the empirical formula, my N value would be 2. A way to rearrange this equation is down here. So your N value is going to be equal to your molar mass for your, specifically for your molecular. It's molecular over empirical, okay? The molecular formula is something that you would have to be given. So this top value of N will be given to you. Because you have to calculate it like experimentally. So don't go searching like on your periodic chart for the top value. You will get that. Now the empirical formula, sometimes it's given to you, or it could be something that you calculated from the previous process, right? You got to this. And now, you know, you want to figure out the molecular formula. So if you're solving for the molecular formula, how many times bigger is the molecular formula than the empirical formula? If the molecular formula's mass is twice as big as the empirical formula, your N value would be 2. If your molecular formula was 3 times as big, it would be 3. So let's try this in practice. So let's say that we have this formula, CH2O. You know that this is an empirical formula because it's the lowest ratio. It says that the molar mass of the actual molecule, though, in real space is 180.2 grams per mole. We want to know what is the molecular formula, and this is for fructose. So remember, molecular formula is going to equal whatever your empirical is. So here's our empirical formula, CH2O, times that N value. We need to find N, all right? So N is equal to molecular over the empirical. Specifically the molecular mass, so that you're not just like, what am I even looking for? Molecular mass over empirical mass. From the last slide, I told you guys molecular mass is always going to be given to you. Okay, so what is the molecular mass? It's the molar mass. Sometimes they call it molar mass, sometimes they call it molecular mass. It's this thing here. All right, so now we know that N is going to equal 180.2, and you can use the units or not, over the empirical mass. Well, where is the empirical mass? It isn't explicitly given to you here, but you have the empirical formula, don't you? So can't we calculate the empirical mass really easy? We just take the mass of a carbon, the mass of 2 hydrogens, and the mass of an oxygen. So what, 16, 17, 18, plus 12, 30? It's approximately 30. So again, molecular mass is going to be given. Empirical mass may be given, or you may have to calculate from the empirical formula, which you guys should be experts at by this point. So now we have an N value that's 180.2 divided by 30. 180.2 divided by 30. And I get an N value of 6. So N for this equals 6. Now, what is that saying? It's saying that my molecular formula is 6 times as big as my empirical formula. I want the formula though. I don't want just the N value. So I actually need to take this number down here and I need to thread it back into that original equation up at the top. So you remember we've got this thing here that tells me my molecular is equal to the empirical times N. So N is 6. So let's just fill that in with 6. And we multiply everything by 6. So C would get a new subscript of 6. H would get a subscript of 12. And O would get a subscript of 6. All right, this thing is 6 times as large as this thing. So when figuring out molecular formula, you first have to figure out N, how much bigger is the molecular formula, and then you thread it back in to actually get the equation. So got it here. Any questions outside of like, we're going to practice a couple of them, where those numbers are coming from? So first solve for N, figure out how much bigger it is, and then plug it in to the, or multiply it by the empirical formula. So let's look at that last problem that we were working on, because there's a second component to it. It says, for number 1, if the molar mass of compound in problem 1 is 110 grams per mole, what is the molecular formula? So remember, we calculated this thing to be what, C3H3O? You know what the molecular mass is. I want you to calculate the molecular formula. So I'm going to give you guys about 3-4 minutes to solve that. First, work towards getting your N value. How much bigger is it than the empirical? And then plug it in. Let's put that over here. Just another 30 seconds or so, and we'll go over it. Okay, so if we're finding a molecular formula is always going to equal an empirical formula times some value n. So you need to either be given the empirical formula or like have solved for the empirical formula in a previous problem. So this is the empirical formula we're talking about. Question 1 and 2 relate to each other. So we've got C3H3O. And if it's the molecular formula, it's going to be this thing times some multiplier n. So we need to get our n value. N is always going to equal your molecular mass over your empirical mass, which is just going to tell you how many times bigger the actual molecule is than your lowest ratio. So your molecular mass is going to be given to you. You should be able to find it somewhere in the problem. In this case, it's right here. So we've got 110 grams per mole. Now, where is the empirical mass? Well, it's not explicitly given to you, but you do have your empirical formula, right? So you should be able to calculate that pretty fast with, 12 times 3 plus 1.01 times 3. Times 3 plus 3.03 plus, we've got 16. All right, so it's roughly 55. I got 55.03 grams per mole. So 110 divided by 55 is going to be an n value of 2. So what that's saying is the molecular formula is 2 times as big. All right, so now you need to take that 2 and you need to put it into this initial equation where we multiply each of the subscripts by 2. So it should be C6, H6, O2. This would be your molecular formula. All right, so first solve for n, then multiply that by the empirical formula. Figure out how many times bigger it is, and then make it that much bigger. Let's see here. I'm just going to pull up this syllabus real quick because I think we are good to go. I'll give you guys one more of those practice, but I just want to make sure we aren't crunched for time. I don't think we are. You guys got a full 2 weeks for chapter 6 because it's a long chapter. Yeah, so we're not starting chapter 7 chemical reactions till next week. So we can do one more of these and then we'll call it a day. So let's do, where was that practice sheet? Right here. Let's do number 3 and number 4. So 3 is asking you to solve for the empirical formula. You have 18.7% lithium, 16.3% carbon, and 65.0% oxygen. So that you want to calculate empirical formula. And then number 4 relates to that problem. It says, hey, here's the molar mass in real life. What's the molecular formula? So I want you to do 3 and then build on to 4. And I'll give you guys about 5 minutes in total for both of those. Okay, so for this one, we had 18.7, 16.3% carbon, and 65% oxygen, most of it's oxygen. So just assume that this is grams for all these. 1 mole of lithium is 6.94 grams. 1 mole of carbon, 12.01 grams of carbon. And 1 mole of oxygen, 16 grams of oxygen. .7 divided by the 6.94. So 2.69 moles of the lithium, 16.3. Come on. 1.36 moles of carbon. And then this one here, we've got 4.06 moles of oxygen. Okay, so we divide by the smallest to get our whole number. So we'll divide it by that 1.36. Hope that we get whole numbers. This first one is like 1.977. That's close enough to 2. This is 1, and then 4.06 divided by our 1.36 gives us 2.98. That is close enough to 3. So Li2, carbon 1, O3. Anyone know what this is? It's lithium carbonate. The second part of the problem was saying, and we know that this is the empirical, right? Empirical. So it gives us the molecular formula 73.8. So our molecular formula is going to equal the empirical Li2CO3 times some value n. Okay, that's the multiplier. N equals molecular mass over empirical. And the top one will be given, and we said it was what, 78? I already 73.8. So this is going to be equal to 73.8 grams per mole. The empirical mass, you've got to calculate from your empirical formula. So you're going to take the mass of 2 lithiums, a carbon, and 3 oxygens. And you get around 73.8 grams per mole. So what is your N value here? It's 1. So we plug that into the formula, and our molecular formula is actually going to be the same thing, Li2CO3, right? The molecular formula is the same as the empirical formula. That happens a lot when you have salts, right? Or a metal combined with some sort of non-metal. So don't be freaked out if your molecular and your empirical are the same, if your N value happens to come out as 1. Any questions on that? Okay. Well, that is the end of chapter 6. Chapter 7 is going to be all on writing equations and balancing chemical equations. And then that'll be chapter 7. And then chapter 8 will kind of combine this chapter with chapter 7. We kind of mush them together. So we'll call it for today. You should be good to go for the homework that's due on Sunday. You've got everything covered. Yeah, if you have any questions, feel free to stay around and ask. Otherwise, enjoy your weekend. And I will see you all next week.